Okay, great. Yeah, so I guess we can get started. This is the last actual class of this course. So hopefully it will be useful. The poster presentations are next week, and the poster presentations, I've given instructions and everything. If people have any questions, I'm happy to take them now or on Piazza or other things like that. Are people basically all set with that? Okay, looks good. So yeah, and then I guess I will get started. So this time we're talking about adversarial methods, and adversarial methods basically are referring to several different types of methods, but they all fall under the same general paradigm. And the basic idea is that we have a model that we want to train or use in some way, and an adversary that works in tandem to learn that model or use that model appropriately. And a lot of people, when you hear adversarial methods, you think about something called generative adversarial networks or GANs. And the model, basically, these are when the model generates an output, such as text, and the adversary attempts to detect generated text. It attempts to detect whether the output has been generated or whether it's a naturally occurring output. However, there's a number of other methods that arguably have had more impact on natural language processing and are still things that I would highly recommend you use today. And these include things like adversarial feature learning, where the model generates features and an adversary tries to distinguish features of different types. And also, there's a concept of adversarial robustness. And this is the same in that we have an adversary where the adversary tries to perturb the input to cause the model to fail. And the model may be trained to be robust to these perturbations. And I'll talk about this, all of these in turn. So first, I'd like to start out with generative adversarial networks. And generative adversarial networks, basically, we can go back to generative models. And generative models tried to model a data distribution P of X or a conditional data distribution P of Y given X. I should fix that. It should be P of Y given X. And then we also had latent variable models that we talked about last time, which is introducing another variable Z and then summing or taking the integral over the latent variable Z. So there's a number of things that a perfect generative model should be able to do. And the first thing is evaluate the likelihood, and specifically have a high likelihood for natural sentences and a lower likelihood for unnatural sentences, or samples, I guess. Another thing it should be able to do is generate samples. So it should be able to, for example, generate a sentence randomly from P of X or conditioned on some other information using a conditional distribution. And it should also be able to do infer latent attributes if it's a latent variable model. So it should be able to do inference like we talked about last time over the posterior distribution. So this might be doing something like inferring the topic of the sentence from a topic model or inferring the latent vector from a VAE like we talked about last time. And no generative model is completely perfect. There are some, this is a little bit old, so you could argue that generation of everything has gotten better since I first created this a few years ago. But basically, non-latent variable models like, regular language models are usually get the best likelihood. They're usually the best at evaluating the likelihood of sentences. They do quite well at generation. And however, they don't really have the ability to do inference of a probabilistic latent variable because there's no concept of probabilistic latent variables within them. There are hidden states, and you could argue that the hidden states in language models are a proxy for latent variables, but there's no formal concept of them. For VAEs, they're reasonably good at evaluating likelihood. They're often slightly less good at generation than non-latent generative models. And for inference, they do a good job of inferring latent traits, especially if you train them using some of the tricks we talked about last time. And then the GANs that we're going to talk about here, particularly with respect to images, a little bit less for text. They don't really have a way to evaluate likelihood. It's hard to frame them as a probabilistic models, so we aren't very good at using them to evaluate likelihood. However, they have some advantages in generation, and arguably can generate better than any model that doesn't have an adversarial component. And in terms of inference, they can also infer latent variables. So why is this? Before I get into this, I'd like to give an example. This is an old example, but it's still, I think, relatively indicative of kind of the traits that an MLE-based model has versus a GAN-based model. And one of the problems with MLE-based models, including either variational autoencoders or just regular, regular non-latent variable models, is that the outputs from maximum likelihood estimation style models tend to be kind of like, what's the best way to put it? They tend to be, in images, they tend to be fuzzy. In text, they tend to kind of emphasize common outputs, or like the typical output that you would have in a particular text. And do people remember the glitter toolkit that I showed before? It was like a visualization toolkit that demonstrated whether a language model was predicting high likelihood words or low likelihood words. I could show it again. If you don't remember, it was this this toolkit, and basically you could see how natural text or language model generated text had lots of high likelihood words, whereas human generated text had more low likelihood words. And so you could argue that the fact that the language model is kind of avoiding generating words with low likelihood is precisely because it was optimized to maximize the likelihood of actual output. So it's kind of trained to be safe and not make any bold decisions about coming up with new content, etc. You might also notice this in if you're using an assisted writing tool of any variety. I use Codex to write code or text a lot of the time, or GitHub Copilot to write code or text a lot of the time. And it tends to give you very generic sounding things. It's very natural, but very kind of generic, very normal sentence structures. However, this is not a bad idea if you're optimizing likelihood, right? If instead of making a bold decision to try to do something new, it makes a lot more sense to just be safe and try to pick, the most likely words to come next. So because of this, you might get an image that looks a little bit fuzzy, because if you made really sharp decisions, but you made them in the wrong place, that would actually lower the likelihood if you got a slightly different image. So you get this kind of fuzzy averaged image. However, if you use an adversarial technique, it prevents this. And in order to understand why that's the case, here's the basic paradigm. You have two models. You have a generator and a discriminator. And basically what the discriminator does is, given an image, it tries to tell whether it's real or not. So it calculates the probability that an image or a text is real. And the generator it tries to generate an output, image or text, that fools the discriminator into answering real. And so the desired result of this training paradigm at convergence is that the generator will generate perfect images that are not at all distinguishable from actual text, from actual images or text, and the discriminator cannot tell the difference. So basically, we want the discriminator to fail in this training paradigm at the end of training. However, at the very beginning of training, it's very easy, obviously, for the discriminator. Like, you know, the generator will be generating, like, let's say we're talking about text, the generator will be generating word salad, or if we're talking about images, it will be generating static that look nothing like natural images. So it's very easy to train a discriminator that discriminates between them. So it's actually hard to reach this state at convergence. So is this clear so far? Any questions or? Okay. Let's get on to the training method. So the training method, basically what we do is we sample a mini batch of data, X real. We sample some latent variables, Z. So these could just be like zero mean unit variance Gaussian variables like we used in the latent variable models before. And then we convert these with a generator into a fake image. So this is exactly the same as like the generator or decoder network in VAs. The difference comes after this, which is now we predict with a discriminator whether these images are real or fake. And then we have this discriminator loss, which is higher if it fails predictions. And then we have a generator loss, which is higher if we get correct predictions on the fake data. And we backprop the discriminator loss to update the discriminator. And we backprop the generator loss to update the generator. So it's actually reasonably simple. Conceptually, the details are more difficult, but the way we express this in equations is we have this discriminator loss function where basically we have a bunch of outputs sampled from the data and a bunch of outputs sampled from the generator. And we basically add these two together and use both of them to calculate the loss. And then the generator loss function, there's a couple of ways to train the generator loss function. One way is to make the generated data be essentially less fake. So what I mean by this is you basically take the opposite of the discriminator loss. You take the opposite of the discriminator loss, or the inverse of the discriminator loss, and try to optimize this. So in this case, these two models are directly competing against each other. And another thing that you can do is you can make the generated data be essentially considered more real. And the reason why you might want to use this instead of this is in the case that the discriminator loss is very, in the case that the discriminator probability is very, one second. So if the discriminator thinks there's a very low probability that the fake data is fake, then this will essentially become 1. And because of that, this log over here will become 0, and the gradients will become very small. And because the gradients will become very small, essentially, you won't learn the generator very well. Not very much gradient will flow into the generator. And so in order to fix this, if this discriminator function becomes 0, in this particular case, log 0 gets essentially you get a lot of gradient flowing into the model, and that makes it easier to train the generators. So because of this, a lot of people choose this particular formulation, despite the fact that this one might be kind of more natural, like they're just directly competing against each other. So, so anyway, this is what this looks like in equations. So one way you can interpret this all is that you're trying to do distribution matching. And so you have essentially two distributions. The first one is you start out with the latent variable according to a very simple distribution, just like in the VAE. And then you somehow transform this distribution to look like the real distribution that you want to model. So you transform P of Z into P of X. And in this case, X is now a random variable with an implicit distribution P of X, which is decided by P of Z and F. And the process can produce any complicated distribution P of X with a reasonable P of Z and a powerful enough F. So this is the same as VAEs also. So VAEs, we take in a very simple distribution and we transform it into a more complicated distribution. However, one problem with this is VAEs make it easy to evaluate likelihood. So like you can actually use VAEs as a method to evaluate likelihood of the data. GANs, you cannot do this. Any idea why this would be difficult to do in a GAN, evaluating the likelihood? What's missing that we had in a VAE that we don't have in the GAN anymore? We've added a discriminator, but what have we taken away?
The prior?
The prior you could probably still would be this P of Z. In the VAE, we also had two models. We had the generator or the decoder model, and what was the other one? Yes, the inference network. So in a GAN, we've added a discriminator, but we've taken away the inference network. And the inference network is kind of really important for evaluating the likelihood of any sample, because otherwise we would just have to sample randomly from the prior, and we might not be able to get any Z's that give you anything close to a reasonable probability for the actual current samples. So that's kind of the connection between VAEs and GANs. And it's also the reason why I said in the previous example here that GANs are not good at evaluating likelihood, despite the fact that they're good at generation. Okay. Cool. So pseudocode is relatively simple. We just sample, generate a fake thing. We get some data from, we get fake data. We predict whether the real data is real or fake given the discriminator, the fake data is real or fake given the discriminator, calculate this function here, and then train G using maybe the non-saturating loss like I talked about before. Okay. So why would we want to do this instead of just training a likelihood-based model? So basically, one reason why is that the discriminator can easily pick up on any kind of discrepancy, including things that are kind of on a more global level. It can easily like point out obvious differences between the input and output, between the real input and the fake, real output and fake output. And another reason why it's good is actually if you do backprop all the way into the actual outputs of the model, the generator now has fine-grained gradient signals to inform it of what and how to improve. So just to give an example, let's say the discriminator somehow was able to pick up on the fact that these blurry eyes here, or this missing ear here, was a clue that this is not a real image. If that was the case, then when you did backprop, that would flow directly into the part of the generator network that was responsible for generating that like blurry place. So that gives you fine-grained feedback. So because of this, essentially, it's a much better way to give you like to pick up on signals that wouldn't be super obvious to pick up on in an MLE-based framework, even with like a smaller amount of data. Any questions about this or discussion? Okay. However, like this is very nice conceptually, but in reality, it's very difficult to apply in practice. It's more so for text, less so for images, but even in images, it can be difficult. So GANs are great, but training is notoriously difficult. So some known problems are with respect to convergence and stability. So essentially, because you have these two competing objectives, they might pull against each other, and essentially the model won't converge well. You'll get fluctuating losses and things like this. There's a number of methods to fix this, like the Wasserstein GAN, which basically changes the objective to be closer to a more global objective in doing gradient-based regularization. A bigger kind of more intuitive problem is mode collapse. And basically what mode collapse is you get a GAN that instead of generating every image in the world, it generates 5 really good images. And so those 5 really good images are impossible to like distinguish from real images because they're actual images. But you're only generating 5 images instead of generating the whole rich like distribution of new images in the world. And so there's a number of methods to do that. Mini batch discrimination, for example, what it does is instead of training the discriminator over a single like image or text, is it trains it over all of the images or text. And by training it over all of the images or text, in a mini batch, all of the images or text in a mini batch. And by training it over all of the images or text in a mini batch, the discriminator can then say, oh, look, you generated the same image 8 times in this mini batch. This looks pretty like suspicious, right? This doesn't look like the actual distribution of images. So that's a way to fix that problem. Another problem is overconfident discriminators. So like right at the very beginning, the discriminator can become very confident that everything is fake, or it can become very confident in its decisions about whether something is fake or not, and that can prevent gradient flow. And there's a couple of methods that can solve this, like one-sided label smoothing. And basically what this does is this causes the discriminator to become less confident in its decisions about fake things. So you basically cause it to predict like not 100% fake, but like 90, 95 or 90% fake or something. So this was all just general stuff with respect to GANs in images, for example, but they can also be applied to text. There are applications of GAN objectives to language, like GANs for language generation or machine translation, dialogue generation. You can see that this was very popular in like 2016 and 2017 when GANs were like 1 or 2 years after GANs were really popular in images. And when trying to apply these to text, conceptually, there's nothing really different other than the fact that you can't backprop through sampling. So it's like the classic problem with latent variable models that use discrete variables, or our training methods where we tried to train towards like blue score or something like this. So here, because this convert with generator part becomes discrete, we can't backprop through it. So basically, we solve this in the same way that we would solve anything else. We can use learning methods for latent variables. And so we can use policy gradient-based reinforcement learning methods, like we talked about 2 classes ago. We can use the reparameterization trick for latent variables, like the Gumbel softmax, like we talked about 1 class ago. And so actually the methods, I mean, it's not like these solve all of our problems, but they're the standard tricks that we use, like what in the other varieties of learning algorithms where these problems crop up. So you should already be familiar with them. The second issue is how to come up with discriminators for like sequences of text tokens. And one way we can do this is there's a number of ways to do this. We can decide whether a particular generated output is true or not. Because many of these works on GANs for text generation were done in 2017, before transformers were really widely used, a lot of them use CNNs. I think transformers would be equally reasonable, but I think it's worth taking a look at how they made a CNN for text sequences. And basically what they did was they did tiling over pairs of like word sequences in the text. And so basically they would come up with a thing that looks at 3 words from this sentence and 3 words from this sentence, and then 3 words from this sentence and different 3 words from this sentence, and form a big tensor, and then compare the tensors together gradually until you put them through a MLP and make a prediction. So for like, if you compare the source and target sentence like this, you could identify places where it seems like you're generating one thing in the target, but there was something like contrary evidence in the source that would prevent, that makes it seem like this is a bad generation. Yeah.
You have X-real and X-fake being included in a discriminative model. Like, does it compare one against the other to check if either of them is real, or is it like they don't get independently?
So it does it independently. So it does it.
You need to have matching input and output.
Yeah. So like basically, the question is, would you want to determine? Would you want to compare 2 outputs and say one is real and one is not real? You could theoretically do that too. I think that would kind of be like, in fact, I think there are methods that attempted to do this for like text sequence generation thing, but it's definitely not the standard method of doing it. It's kind of like a, yeah. See, it actually seems like a reasonable strategy in the case that you want to be upweighting the real thing and downweighting the non-real thing. I think a lot of the theory about why GANs are good, like generative models, would not hold in that case, but still, like maybe heuristically, that seems like a good strategy. So, yeah. Another thing that I should mention is actually, when I saw this glitter work, which came out after, like, essentially this came out after a lot of the GAN, for text generation work, but you could almost train a discriminator on this, like, top 10 entropy histogram. So you see this top 10 entropy histogram over here. It looks very different, or it maybe top K count would be even better. This top K count image is like quite different between generated text and in real text, right? Wait, let me show you the real text. Yeah, so here we have the real text, and here we have the generated text. And just by looking at this top K count, you can tell which one is real and which one is generated, because the real text has a lot more like low frequency words. So what I want to say is, you could also become creative in how you train your discriminator. You could also just train a discriminator on the frequency histograms. And if you did that, then the generative model would be explicitly encouraged to generate frequency histograms that looked more like actual text. And that would maybe result in a more creative language model that did, more surprising or unexpected things. And then if you also had a discriminator to try to discriminate between like natural and unnatural text, or you also added a maximum likelihood objective, you might be able to come up with something that would be both like fluent and, like more creative or something. So you don't need to be stuck with a CNN or transformer as your discriminator. You could also come up with other more creative things. Okay. So one problem is GANs for text are hard. They're even harder than GANs for images. And the reason why is because all of the difficulties, like many things that have to do with text, all of the difficulties in images exist there, and there's some additional difficulties. So what type of discriminator do you use? I think this was essentially a problem that they encountered where if their discriminator was too strong or too weak, essentially they had trouble learning the model. They might also have been able to fix this with one-sided label smoothing, which I don't think they used, but they encountered that problem. Also, the strength of the discriminator before they started training the generator caused a problem. Another thing is the learning rate for the generator with respect to the discriminator. Learning rate for the discriminator with respect to the generator. All of these hyperparameters are added in addition to what you would normally have for MLE. So there are some stabilization tricks that you can use. One is assigning rewards from the discriminator to specific actions. And this is actually, I don't know if I talked about reward shaping in the reinforcement learning lecture. Do you know if I did this? Okay. So this is a general trick called reward shaping. And basically what it is you assign a reward for partial sequences. So like you might do a discriminator at the end of each partial sequence, like D this is, D this is, and still the discriminator thinks this is like a real sentence. And then you get to this is a fake, and suddenly the discriminator realizes this is a fake sentence. So the fake probability goes way up. And then you get this is a fake sentence, but the model already thought the sentence was fake. So the discriminator probability stays high. And so if you do this, you can then assign a reward specifically, or assign basically a negative reward specifically to the place in the sentence where this is a fake, the place in the sentence where the discriminator probability went up. And this can also be done in other cases of applying reinforcement learning to like sequential predictions. So for example, if you're learning a model to optimize something like blue score or any other evaluation metric that you want to evaluate, you can also evaluate how much blue score goes up each time you generate a word, or how much the evaluation metric changes each time you generate a word, and give a greater reward when you generate a reward that causes something to go up. So I remember I did talk about this a little bit in the reinforcement learning lecture, where I talked about getting a reward right at the end, like after you've taken all of the actions is the worst way to do things. But reward shaping is where you specifically like design your reward to give intermediate feedback in an appropriate way. Other tricks, performing multiple rollouts. This is standard from reinforcement learning. So you just do multiple rollouts. Like you do multiple samples from the model and get a reward for each of them. Another interesting thing that people have done is instead of doing discrimination, instead of training a discriminator over instead of training a discriminator over the actual discrete outputs of the model, you train a discriminator over the results, over like the logits or the results of the softmax. And so basically you have X, from X, you calculate the hidden states, and then you calculate the probability of the output, and then you calculate the actual output, and you do the adversary over the intermediate state. The obvious reason why this is nice is this is differentiable, right? You're not doing any sampling, or the sampling operation is not in the middle of the computation graph that you need to be backpropping through. However, the softmax results actually do provide you all of the information about what Y is going to be, at least in the case of greedy decoding. So if you're doing greedy decoding, you're guaranteed that Y is going to be the result of like argmax PY. So this is just a deterministic transform, I guess. So this is strictly as, or maybe even more expressive than doing discrimination over the actual like outputs here. So I think this is a really nice trick if you want to use like essentially GANs in training textual models. Any questions about this? One thing I should point out is this is not super widely used nowadays because of the stability problems that you have in training them. So like, however, I do think it's really, powerful, and like a lot of the problems that people point out with text generation models, like they're bland or they're repetitive or other things like this, you could potentially fix with these types of methods. So it's worth knowing about. Now something that's more immediately practically useful, it's something that I've, like actually used in my work relatively frequently and sometimes recently, is adversarial feature learning. And basically here, the adversaries are over the features of the model instead of the outputs. And so in GANs, you have the adversary over the output Y. In adversarial feature learning, you have the adversary over the intermediate states H. And why would you do this? This can be applied to non-generative tasks. So it can be applied to tasks where you're just doing like binary classification or something like this. And you can also do it over continuous features, which is much easier than discrete outputs. I've actually talked about this briefly before, but I'm going to reiterate it again now because now we have the full context of, like adversarial methods, which is learning domain invariant representations. And so essentially, I've already shown this before, so I'll do it very quickly. But like, let's say we want to learn a sentiment classifier that works equally well for, movies or for books or for apartments. And if we do that, then we train a sentiment classifier in the normal way, and then we train a domain discriminator. And we basically try to fool the domain discriminator while still being able to do like sentiment classification, for example. There's also interesting applications of this for like sim to real transfer, which is where you create a simulator that has simulated data, maybe, or you do data augmentation of some variety. And if you do that, then you can have basically a classifier trained on this like data augmented data, but then you also have a domain discriminator that tries to tell whether the data is real or fake, and you try to fail this real or fake discriminator. And what that will do is that will put the data augmented data into the same space as the real data. And so that could, improve your performance over domain augmentation. Also, for a practically useful application in industry, for example, very often you'll have an annotated data set that's 5 years old. And you want your 5-year-old data set to remain useful today when you're training a model and not have your performance gradually degrade because your data is out of date. And they also demonstrated that this type of method can also be done by having like a time classifier. And try to fool the time classifier to put the things from different times in the same space. can do a similar thing for languages. So you can try to put language representations in the same space. For text classification, you have a like English or Chinese classifier that you try to fool, and a sentiment analyzer that you try to train. It has also been used for other multilingual techniques like multilingual machine translation, for example. Yeah.
Joint feature extractor.
So a joint feature, the joint feature extractor is up until a certain point, you just extract features from the sentence. So this is could be a transformer or any other type of sequence modeling model. And then you have a few extra layers, maybe MLP layers or something like this. On top, one MLP layer tries to distinguish sentiment. Another one tries to predict like the language. But you try to fool the language predictor and try to learn the sentiment predictor. And the gradients from both of these tasks flow back into the joint feature extractor. So the feature extractor in the end will extract kind of language invariant features that nonetheless can still allow you to predict sentiment.
What does the joint part mean? Like, how are you collating or combining the two features from each language?
So basically, yeah, maybe this is a little bit confusing. I actually copy pasted this directly from the from the paper, so don't blame me about it. But you run this independently over English text and Chinese text, so it's not run jointly over both texts. The reason why I think they're calling it joint here is because it's the features extracted from this are used both for sentiment classification and for the adversarial objective here. So I think that's specifically what joint is referring to. Or maybe it's referring to the fact that this is a feature extractor that can be used either on English or Chinese. Both of those are the case, but it's not for both at the same time. Yeah. Yeah.
Is there a reason like why the model doesn't, like if we didn't use like those invariant representation techniques, is there a reason why the model doesn't directly learn those invariant features?
Yeah, very, very good question. And I could actually show you a visualization from one of our papers. So in this paper, we basically examine whether independently learned features, when you learn features on multiple languages, whether they're learned, and these are actually just for word embeddings, but it's actually similar if you're talking about contextualized word embeddings. But vocabulary that appears in both languages tends to appear in both languages, gets learned in one part of the space, but vocabulary that tends to only appear in one of the two languages gets kind of put in different parts of the space. And why does this happen? If we think about it, if we think about the objective that is used for like pre-training or something like this, basically the pre-training objective is trying to predict whether, given the surrounding words, a particular word is likely to appear. And given that, it's extremely unsurprising that Chinese words or Spanish words and English words would be in a different part of the space, because it's very likely that if you have surrounding Spanish words, you're going to have a Spanish word. So that's like really important information to have. And so there's actually a pressure to put them in different parts of the space if you're using a pre-trained model. If you're not using a pre-trained model, and you were just randomly initializing the word embeddings and training the model from scratch, I think it's not that there's any reason why it's not that there's anything preventing them from being in the same space. It's just that there's nothing encouraging them being in the same space either. So they kind of, will just independently go into different spaces, and there's nothing like encouraging them to be similar, I guess. And if you encourage them, they'll overlap. So here, we actually tried aligning these spaces together using an adversarial objective. And after you do this, you get them in the same space. And then like the resulting word embeddings are better for downstream tasks and for transfer and stuff like that as well. I don't think I cited this paper in the presentation, but if you're interested, you can take a look. Yeah.
Well, using more number of languages might encourage like the model to push them in the same space because they can't learn so much. There's like too many languages, they can't push everything to a different space and try to learn so much.
So, good question. The question was, if you use more languages in multilingual learning, will that encourage them to be in the same space? And because the model capacity doesn't allow them to be like in different parts of the space. So I think there's a lot that you could talk about this in the multilingual context, and it's maybe a little bit beyond the scope of this lecture. But one interesting thing is, despite the fact that there's like little pressure for them to be in the same part of the space, zero-shot cross-lingual transfer still works, right? You train a big BERT model on 100 different languages, and you can then train a part of speech tagger on English, and then it just works on Chinese or something like that, which is really, really strange, maybe. But there's actually a reason why it's not like, it kind of makes sense. And this is my favorite example. So if I go to the Wikipedia article for Carnegie Mellon University, and then I click on the Chinese version, you're noticing Carnegie Technical School, Carnegie Institute of Technology, Richard Sayert, Purnell Center, Doherty Hall, lots of other stuff like this. And so you can see that even in like Chinese, there's a lot of English, right? And probably if you looked at different Wikipedia articles, there's lots of other languages. So the words tend to be in a different part of the space, but not so different that, cross-lingual transfer wouldn't work. However, if you used an adversarial objective, it'd probably be even better. So, yeah. And there's actually papers discussing this more, but it's a bit beyond the scope of what we're talking about here. Okay. Cool. Another thing is adversarial multitask learning, and this is a kind of neat trick. The basic idea is when we're doing multitask learning, we might want some features in a shared space across tasks, others separate. And so basically what they do is they have a shared and private model where they have some features that are shared and some features that are not. If you have a really large model, you could arguably also just like have an adversarial objective over just some of the features and then leave the other ones to not have an adversarial objective over them. And so, oh yeah, sorry. In this particular case, the adversary is a task discriminator. So it tries to just discriminate like which task you are handling to learn task invariant features. Oh, sorry, going back to the question about shared features versus not shared features. I think there is actually a lot of, in multilingual models, I think there's a lot of evidence that suboptimal sharing is happening. So like, essentially, even if you're training a model that has lots of, even if you're training a model that has like lots of parameters, essentially the parameters for different languages get pushed in very like different parts of the space. So, or the parameters that are active when processing certain languages get pushed into very different parts of the space. So I think that's an argument for trying to do this sort of learning. So then another technique that exists is something called professor forcing. It's a play on words for teacher forcing. Basically, this is halfway in between a discriminator on discrete outputs and feature learning. And so what you do is you generate the output sequence according to the model, but train the discriminator on hidden states. So this is instead of training it on the probability output by the softmax, you train it directly on the hidden states. So that's just another option. In fact, I probably could have put that in the previous slide where I talked about training on the probabilities, but it's just whether you train it on H, whether you train it on the probability of Y, or whether you train it on Y. Okay. So another thing that you can do is you can do unsupervised distribution matching. And to give one example, this is actually something that I kind of started talking about last week, but I'm going to talk about it in more detail this week. And this is unsupervised style transfer for text. And unsupervised style transfer, basically what it does is you want to transfer sentences with one style to another style. And it actually might be not entirely accurate to call this style transfer, because style in linguistics, what it means is essentially different ways of saying the same semantics, saying the same content. So for some of these things, it's actually not necessarily style transfer. It's maybe content transfer. But some examples, decipherment are translating ciphered sentences to natural sentences. So like, let's say you randomly replaced each word in English with another word. Like reproducing the original English sentence. Transfer sentences with positive sentiment to negative sentiment. This is not style transfer. This is changing the content. So other people have called it attribute transfer, which might be more of a mouthful, but more linguistically accurate. Another thing is word reordering. And so this, yeah, actually, sorry, I should have had a slide for explaining the style transfer task. Some other examples of style transfer that a lot of people do are like formality, formality transfer, things like decipherment, dialect. Also, arguably, translation could also be considered style transfer because, you know, the content is the same, you're just saying it in different languages. So does anyone else like have any examples of tasks? I realize I should have had a slide on this, if you're familiar with this. No, okay. If not, that's fine. So anyway, basically the way this works is you have a model that tries to discriminate between two different styles. So specifically for formality, which I think is the nicest example of style transfer because it's something that actually could be quite useful. There's data that exists for it. Oh yeah, sorry. I remembered the first example of style transfer, which is like, it's a subset of dialect, but they basically did Old in English and modern English Shakespeare, Shakespeare plays. So they took the original Shakespeare and like the modern interpretation. So you have like Shakespeare, English, and then modern English. And then for formality transfer, you have like formal into informal text. And so in this case, you have a discriminator that tries to discriminate between the two styles. If you have lots of examples of formal text and informal text, you could even just like pre-train the discriminator to determine whether the text is formal or informal. And then you essentially train a model in an unsupervised fashion to try to generate an output. And after you've generated the output, you need to do two things. The first thing you need to do is you need to pass the discriminator test. So essentially you need to fool the discriminator into thinking you're of the other style. So let's say we're doing informal to formal translation. So we translate from informal to formal, and the formal output needs to fool the discriminator into thinking it's formal. And then the second thing you need to do is reconstruction. So you need to reconstruct the original output. And by having these two objectives, essentially what that forces you to do is that forces you to translate into the other style, but also keep all of the content so you can reproduce the informal style when you go in the opposite direction. And this also, you need something like reinforce or like policy gradient methods or something like that, because you're generating a discrete output and then calculating a reward over it. Another example is unsupervised alignment of word embeddings. This, when it first came out, was like kind of shocking, a shocking result to me. Which is if you have word embeddings that were completely independently learned in two spaces. So you basically train some word embeddings on English and then train some word embeddings on Spanish. You define a function to map between the spaces. And so basically maybe you do a linear transform between space X and space Y. And so you do X times W. You might also add an additional constraint that the transform is orthogonal. And after you do that, you have an adversarial. In the way you determine this transform, or the way you learn these the parameters of W, is just using an adversarial objective. So you essentially just try to optimize these to fool a discriminator, so the discriminator can't tell whether any of the individual points came from Y or came from WX. And you use no other signal, and nonetheless, this is good enough so that many of the nearest neighbor points between WX and Y have the same meaning. So why is this possible at all? Like, it's very strange. You have no actual alignments between like English and Spanish, yet you can learn an appropriate transform so that like the nearest neighbors become the same words. Any ideas why? What sort of characteristics of language or individual words would allow you to like get a hint about which words corresponded to which other words, even if you were given like a old tablet of, or maybe lots of old tablets of Egyptian hieroglyphs or something like that. Hieroglyphs don't count because they actually look like things. So, a big printout of lots of words in Turkish or something. Yeah.
Context.
Yeah, context, and more specifically,
Adjacency to other words.
Adjacency to other words, yeah. So certain words appear adjacent to other words, and that's going to be constant across, different languages, because in different languages, still topically, groups tend to cluster, words tend to cluster together. There's one other really important thing. What's the other thing about words that tend to appear in different languages?
The distribution within a language in terms of meaning will remain roughly similar to in whatever language.
Yeah, the distribution with respect to meaning remains roughly similar. I think that's also part of the reason why they group topically, but I think that will largely show up in like the topical groupings. One other really important thing. So like, let's think of the words cat and convolutional. What's different between them? That you could know, like you could guess by just like looking very briefly at a very large corpus. Length of the word is good. Okay, let me think of something else. Cat and DAG, D-A-G, like directed acyclic graph. Context is one thing, but we already talked about that.
Meaning itself is like
Yeah, the meaning is different, but we that will show up in topical groupings. Bob knows, but I'm not going to let him answer. It's something pretty simple. You could probably get it from a bash command line script.
Frequency.
Yes, frequency, exactly. Yeah. So words that tend to be frequent in one language will tend to be frequent in another language. Words that tend to be infrequent in one language tend to be infrequent in another language. It's not a one-to-one correspondence, of course, and there's lots of details that go into it, but overall that's the case. So basically what you can say is, okay, these words group together. This one is the most frequent word in that group. These words group together. This one is the most frequent word in that group. And somehow these two traits are like enough to help you map using an adversarial network, which kind of shows how powerful these things are also. And so once you do that, there's a bunch of other post-processing that you can do, like you can find nearest neighbors and then do supervised training to further improve your accuracy. But the basic idea is just mapping the two distributions together. And so you can further expand this to unsupervised machine translation, where you basically use cycle consistency, doing a very similar thing that I talked about before. You map into one language, you have a discriminative objective, and you have a reconstruction objective, and you optimize the unsupervised machine translation to do this. One of the tricks, there's a bunch of little tricks that they put into doing this, but one of the big tricks is that you initialize the unsupervised machine translation system with a word-by-word translation using these embeddings. And so you first learn the embeddings. That's kind of like a bilingual translation dictionary. And then you map the embeddings to be like kind of word-by-word translation sequences between the two languages. And then you further refine it from there to get more natural outputs. And this isn't like good enough to build a production translation system in any language. It does like a lot of silly things like mess up content words and stuff. But the fact that it works at all is like quite impressive, I guess. So, the final thing I'd like to talk about today is adversarial robustness. And this is another really important topic. It's a little bit different than the ones I talked about before, but it's similar from the point of view of having an adversary. And so before we go specifically into adversarial robustness, we can go into like gist robustness. And this is in this particular case, this is the sensitivity of a neural machine translation system by like the 2 character level perturbations.
I could read it actually.
Yeah, so this input
Very screwed up German.
this is very screwed up German. So basically what they did here was they like perturbed the text. This is a famous example also from English, where basically you have like, according to a study from Cambridge University, it doesn't matter which order the letters in a word are. The only important thing is that the first and the last letter appear in their correct place. And then you can perturb all the internal letters in the word and still most people can read it appropriately. And so they basically did the same thing in German and then tried to translate this, and all of the like translation systems basically like completely fell over and were not able to translate it all. And
I'm surprised and pleased I can read the German.
Yeah. But nonetheless, Bob can read the German, and if it were in English, we would all be able to read the English. And so basically what they showed is as they added more change, just the machine translation systems got worse and worse. And this was independent of whether you had a character-based system, a word-based system, a subword-based system. And so this is an issue. More interestingly, this was just adding random noise, but if you add adversarial noise, this is noise specifically designed to break systems. And so essentially what you can do is the easiest thing that you can do specifically for fully differentiable inputs like image classification systems is you do backpropagation, but instead of backpropagation into your parameters to minimize your loss, you do backpropagation into the input to maximize the loss. And so, yeah, actually, so this is, if you're more interested in this, you can also see this wonderful tutorial by Zico Coulter from CSD. But the most famous example here is the example, like we have a pig that I think most people in this room would agree is a pig. And they add a little bit of noise on top of this pig. So now this pig has some noise on top of it. And I think most of us would not notice this pig has noise on top of it. And, or wait, sorry. Okay, this is the one with noise on top of it. So this is the noisy pig. And this is the mask that they applied to the pig, but they multiplied it by some very large value. They multiplied it by 50 to like show what has changed in the mask. Normally it would be basically invisible to the eye, and you can see that it's now classified as a wombat, which is not a pig. You know, it kind of might look a little bit like a pig. And so you say, pig, wombat, they're basically the same thing, close enough. I don't really care. But then they decided to make a targeted attack where they also added a noisy mask. Here's the noisy mask. And now this pig is classified as an airliner. So nonetheless, we all think this is essentially a pig. You know, basically you can trick a neural network into, you know, thinking something else. And they had this horrible pun that by adding a small mask, they made this pig fly. Like the saying when pigs fly. But yeah, it's an amusing tutorial. You can take a look at that. But anyway, so this is more difficult for text because unlike images, it's very hard to come up with a like minuscule perturbation to text that doesn't change the semantics of the text at all, right? So here are some examples from a traditional, from like one of the first papers on adversarial inputs for text. And this is the source. So it's German, and one of the things in here is Augusta, which is, I guess, the name for Augustine. And they added a few characters. So they figured out a few characters that they could add to flip the, to like maximally decrease the likelihood of the output. And in the result they get in 1931, a woman named Rutgers was brought into the medical institution in France. However, these are like different things, right? Like these are different words, and you can't just easily flip one character and make it the same word. Here's another example. They added like a 6. They added or replaced a C with a 6 in psychotherapist and made it mess up. And replacing a C with this, oh yeah, and they moved around some letters too. And basically, like this is very noticeable, right? Like unlike the pigs where we all just thought they were pigs, this is like quite obvious. So what is an adversarial example? This is a paper that my former student Paul Michel did. But basically we tried to define adversarial examples for text as things that are meaning preserving on the input side, but meaning destroying on the target side. And so like source meaning destruction is basically when the similarity between the meaning of the source goes down a lot. And target meaning destruction is when the similarity between the, or actually I'll show that here. So target meaning destruction here is when the similarity between the reference sentence and the actual model output goes is much higher than similarity between the actual output and the adversarial inputs resulting output. And so basically what we're saying is like if the similarity is going far down on the target side, but it's not going down very much on the source side, that's a good adversarial example for text. Meaning here is defined by some metric of semantic similarity between the inputs and the outputs. We intentionally left this underspecified, although we did try a few of them in the paper. But the important thing here is that it doesn't matter how we measure semantic similarity, this definition will still hold. So if we get a much better model of semantic similarity in the future, then we could just swap it in here and the same, equation would still be relevant with respect to defining adversarial examples. So this is nice. Another important concept is adversarial training. And what adversarial training is it's basically training your model to be robust to adversarial examples. And the way it works, the simplest idea is you sample adversarial examples at training time and make sure that they're also handled correctly. So essentially, one thing that you could do is if you're trying to train an image classifier, you could just find the nearest adversarial example that doesn't make a big change to the input, and make sure that that also gets a good loss on classifying the target. There's lots of theory about this, and actually one of the interesting pieces of theory is that this is kind of like the optimal training strategy for adversarial robustness. There's no better training strategy to achieve adversarial robustness than just sampling the best adversarial example that you have and training on that example. And yeah, there's a link to the tutorial. I have one kind of timely thing that I just thought of because I was looking at, I was thinking both about the fact that I'm going to be teaching this class and about ChatGPT just being released. So I posted this on Twitter earlier today. And so OpenAI released a ChatGPT model that a lot of people are playing with. Maybe people have seen this. And essentially, in the first 24 hours of everybody using the model, everybody was just trying to break it. So they were giving like lots of adversarial examples. So now OpenAI just has to train their model on all of these adversarial examples and they'll achieve like optimal adversarial robustness. And not only are these adversarial examples like, they're like better adversarial examples, right? Because like humans were thinking of all the crazy things they could do to break the models. So if you were playing around with the model in the past 24 hours, thank you for giving OpenAI free training data and making the difference between them and anybody else like even wider. So, cool. Yeah, that's all I have for today. Any questions? Yeah.
The discreteness issue about it being harder to do this with NLP than pictures.
Yeah.
I wonder if it's not really on NLP, but like on the picture side of things, like the reason why none of us think that's an airplane is because we have these substructures and like there's a lot of discrete parts that we derive from the image.
Yeah.
So if they did that in the image world, that might actually make it harder to adversarially rep things.
So let me try to rephrase was that a comment or a question?
I
Yeah,
guess it's fine,
a thought, yeah. So basically, the reason why it is easy to adversarially attack image models is because the image models are based kind of more on surface features as opposed to like recognizing individual parts and like putting them together. Yeah, so the promise, like interestingly, like the promise of deep learning was kind of like that the lower layers would serve as feature detectors and then the upper layers would serve as like high level combinations and stuff like this. The existence of adversarial attacks like this kind of like says, well, maybe that promise wasn't entirely like realized. And, you know, in fact, these feature detectors are like shooting off when they shouldn't be and stuff like that. So yeah. So that being said, I think in general, better models tend to be more robust as well. So you know, there's that too. Any other? Yeah.
Like inside like the multilingual low resource setting, is learning like invariant features a common way to improve the fairness across different languages?
Is learning invariant features a common way to improve fairness across languages? I'd say it's a moderately common way of doing this. Like there definitely has been quite a bit of work to do this. And in general, it leads transfer to be better, which kind of helps all languages, but particularly languages that had low accuracy in the first place. So yeah. Cool. I don't see any other hands, so we can finish up. That's the last class. So thank you for joining, and I'll see you at the poster session.